残酷な天使のように少年よ神話になれ青い風が今胸のドアを叩いても私だけをただ見つめて微笑んでるあなたそっとくれるもの求めることに夢中で運命さえまだ知らない痛いけな瞳だけどいつか気づくでしょうその背中には未来目指すための羽があること残酷な天使の手で窓辺からやがて飛び立つほとばしる熱いパトスで思い出を裏切るならこの空を抱いて輝く少年よ神話になれ
What is math? Where does it come from? What is math made? Why am I so good at it? How can mirrors be real if our eyes aren't real? Oh, hello! Let's get into it. Okay, everyone, we're back, talking a little bit more about what the derivative tells us. So last time we learned a lot about what the first derivative tells us. We learned that the first derivative tells us when a function is increasing or decreasing, and that by using some tests coming from the first derivative, namely the first derivative test, we can discern where a function has a local maximum or a minimum, and via isolating this minimum or maximum in an interval, we can determine absolute maxima and minima just via comparison. So we're on to talking about the second derivative. Here, we're going to start out by talking about concavity and inflection points. So let f be a differentiable function on an open interval I. So something like AB, not something like AB with the brackets. None of that here. Okay, if f prime, the derivative of f, is increasing on the interval I, then we're going to say that f is concave upward on the interval I. If f prime, the derivative of f, is decreasing on I, then f is concave downward on I. If f is continuous at a point C, and f changes concavity at C from up to down or vice versa, then f has an inflection point at C. So, three basic concepts, two of them almost the same. One of them is concave upward. This is when the first derivative of f is increasing. Since f prime, the first derivative, measures the rate of change, this is saying that the function's rate of change is increasing. This doesn't necessarily mean that the function is itself increasing. It could be decreasing at an increasing rate, if that makes any sense. Similarly, if we have concave downward, this tells us that the derivatives, the rate of change of f is itself decreasing. So this is measuring how f is changing, and concavity is measuring how the rate of change is changing. This seems a little bit confusing. Luckily, it's super easy when we look at a picture. Let's try it out. Okay guys, so I've got a nice graph of a parabola here. Just a classic parabola, x squared, graphed on out. Okay, let's consider some information provided by the first derivative. So if we look at the first derivative, that's just 2x. We can see that the first derivative is above the x-axis. That is, it's got positive outputs. to the right of 0. So on this chunk over here. Okay, notice this corresponds to places where the tangent line would have a positive slope, since the first derivative tells us the slope of the tangent line. That is, to the right of 0, this is the places where the function is increasing. As I go rightward, I'm going upward. Similarly, to the left of 0, my function is decreasing as I go rightward. I'm putting in bigger inputs as I go to the right, and I'm getting out smaller outputs, lower and lower on the y-axis. Naturally, this would mean that my tangent line has a negative slope, and so my derivative is below, the graph of my first derivative is below the x-axis. It's negative slopes. All right, what about the second derivative? That's just going to be 2. That's just positive everywhere. Huh. Okay, so let's notice something here. A parabola, if you'll grant me this, sort of looks like a bowl pointing upwards, like a cup facing up. Does that seem right? Yeah, seems fair. Let's look at another graph. Okay, now we're looking at the graph of y equals negative x squared. The exact same as before, just flipped upside down. So, if we graph the first derivative, we see that we get minus 2x, and hey, wouldn't you know it, just the sign of it has changed. So before, when we were looking at the parabola pointing upwards, the first derivative was positive to the right of 0. Now it's negative, and vice versa to the left of 0. Okay, so this guy, if you'll grant me it, looks a little bit like a cup facing down, like a bowl upside down, yeah? If I graph the second derivative, which is just negative 2, notice, this guy, it's negative everywhere. All right, you might be saying, Bryce, what are you even talking about? Let's go on to the next example to really drive it home. Okay, here I've got the example that's going to make everything clear. Here I've graphed a cubic. This is a lot more complicated of a function, all things considered, than the parabolas we were previously looking at. Just for ease and convenience, better graphing, I've chosen the cubic 1/3 x to the third minus x. It's got these two nice little bumps on it, and it doesn't get way too big and crazy. It's not too narrow, anything like that. So we take a derivative, and we'll get x squared minus 1 as the first derivative of this function. This is a parabola. Notice this guy passes through 0 at -1 and at 1. Just trace on up to the graph here, and notice that that's at a peak, and over here we're at a little valley down here, yeah? That's the top of a hill and the bottom of a valley. So this is what we learned yesterday. When the first derivative is 0, that certainly, in many cases, corresponds to a critical point of our function, and in this case, it corresponds to some local maxima and minima. Here's a local max, there's a local min. All right, cool, good enough. Now, if I throw in the second derivative, suddenly something changes. So notice here, I'm going upward as I go to the right on the number line, and then right in this little region, this is the only place where I'm going downwards. Yeah? Going downwards in here, and then I'm back to going upwards. And so the little chunk below the x-axis on the first derivative, that's measuring that place where I'm decreasing, where I'm going like this, or I'm going down. But notice that first derivative, it's got its own critical point right down here, yeah? And that seems to correspond to this guy right here, where it looks like my cubic is changing from being like a cup facing down to a cup facing up. Okay, let's make everything kind of messy by putting a third graph on and plot the second derivative. Bam, 2x. Easy second derivative. Notice 2x the second derivative is changing from negative to positive precisely when my function, my original cubic, is changing from being like a cup facing down to like a cup facing up. It's basically acting like those two previous examples with the parabolas glued together at this point. And notice that's exactly what the second derivative is picking up with its zero. When the second derivative is zero, that's telling us that our function is changing from being downwards pointing like this cup down, to like this cup facing up. This is precisely the notion of concavity. And notice, if I get rid of my original function and just look at the first derivative and the second derivative, this is just the story from yesterday. It's exactly the same story. My function is decreasing, and then it's increasing. This is what this is measuring. I've got negative values here. That corresponds to negative slopes of tangent lines. I've got positive values over here. That's positive slopes of tangent lines. And right at that global minimum, which also a local minimum, I have precisely the zero of that derivative. So since the second derivative is, and this is confusing to say, since the second derivative is just the first derivative of the first derivative, really everything from yesterday just carries through. We're just going to do it one more time. All right, cool. The interesting thing is that this has an interpretation in terms of the original function. It measures what kind of a cup it is. That is, it measures concavity. So this function is concave down here. CD, concave down, like a cup facing down. Here, it's concave upwards, like a cup facing up. Good enough. Let's go further now that we've got some intuition. Okay, now let's start with the first theorem. Theorem 11. Test for concavity. Let's suppose that f prime exists on f double prime, the second derivative, exists on an open interval I. If f double prime is positive on the interval I, then f is concave up on I. If f double prime is negative on the interval I, then f is concave down on that interval. And if c is a point of I at which the second derivative changes sign, so at c, f double prime is changing sign from either positive to negative or negative to positive, then that is an inflection point of f. That is a place where f has an inflection point. So that's places where I switch from being like a cup facing up to a cup facing down. Something like this. It's that little bend, that little spot where it bends and it changes what it's doing. All right, let's do an example. Okay, example number 10. We're going to use a familiar function, one we used in the last video. So let's identify the intervals on which the function f of x equals 3x to the fourth minus 4x to the third minus 6x squared plus 12x plus 1 is concave up or concave down. Then we're going to locate all of the inflection points. That is, we're going to locate all of the places where this function changes its concavity. So, like I said, we considered this guy in example 6 in part 1 of this video, where we found that the first derivative, when we factored it all out, was given by f prime of x equals 12 times the quantity x plus 1 times the quantity x minus 1 squared. So, just doing a little bit more deriving, it follows that the second derivative, f double prime of x, is 12 times x minus 1 times the quantity 3x plus 1. So if you want to see this, we can run through it really quick together. Let's try it out. It's a little bit of a doozy. It just takes a bit. But so we know that f prime of x is given by 12 times x plus 1 times x minus 1 that whole quantity squared. So when we take the second derivative, we just derive the first derivative again. That 12, that's just going to sit right there. So I'm going to put a big parenthesis, just leave that 12 outside. We're going to derive the first thing, leave the second thing, put a plus, write the first thing, and derive the second thing. Classic old product rule. So the derivative of x plus 1 is just 1. So we pick up that x minus 1 squared, and then we add on x plus 1, and we derive x minus 1 squared. The derivative of x minus 1 squared is just 2 times x minus 1 times the derivative of x minus 1, which is just 1. So we're good to go. We can just wrap that off there. And now all we got to do is just go on through and do a little bit of factoring. So 12, I've got an x minus 1 in both of these terms, so I'm going to pull one of them out, x minus 1. And now I've just got an x minus 1 in the first part by itself, plus that x plus 1's just hanging around, but it is getting multiplied by that too. Okay? A little tiny bit more, x minus 1 plus 2x plus 2. Okay? So that's just going to turn into 12 times x minus 1 times x plus 2x, that's 3x, minus 1 plus 2, that's just plus 1. Hey, there we go. Same thing we got right here. So 12 times x minus 1 times the quantity 3x plus 1. There we go. So from this, we can pretty easily see that f double prime of x is equal to 0. The second derivative is 0 when x is 1 or when x is negative 1/3. These points are just candidates for inflection points. We have to actually check that the function changes concavity. So we have to determine whether or not the first derivative changes signs. The second derivative changes signs. So if we throw in a point, less than negative 1/3, maybe we could throw in minus 2. Let's try it out. 3 times minus 2 plus 1, that's negative. Minus 2 plus 1, it's going to also be negative, so positive, negative, negative, it's positive. So we find that the second derivative is greater than 0, and f is concave upwards because of this on the open interval from negative infinity up to negative 1/3. We could throw in a point between 1 and infinity. Maybe let's throw in 2. 3 times 2 plus 1, that's positive. 2 minus 1, positive. So we got positive, positive, positive. Once again, on the open interval from 1 to infinity, f double prime of x is positive and f is concave up. Similarly, if we pick a point between negative 1/3 and 1, a very easy one would be 0. We'll get 12 times 0 minus 1, that's negative, times 3 times 0 plus 1, that's positive. So we got positive, negative, positive, that's negative. So f double prime is less than 0, and f is correspondingly, because of this, concave downwards on the open interval from negative 1/3 up to 1. That is, f double prime changes sign at negative 1/3 and at x equals 1. So the concavity of f also changes at these points. Therefore, the inflection points occur at x equals negative 1/3 and x equals 1. Now, some people go with the convention that the inflection points are always points on the graph. If you want to go with that convention, you're just going to plug in negative 1/3 into f. That'll be the y-coordinate. And then you'll plug in 1 to f, and that'll be the second y-coordinate. In that case, you could write the inflection points in that way, but I don't see any reason to go through that extra work. So, since this is kind of a new concept, let's look at another graph. Okay guys, we're looking at the graph of that function. So it's this weird looking guy. We looked at it yesterday. Let's double check to make sure that everything is making sense here. So we got a function that looks like a cup facing up until just about in here-ish. Maybe somewhere about minus 0.33, something like that. Right around here, it switches from being a cup opening up to a cup opening down, albeit a very shallow one. Okay, easy enough. And then if I keep going up to 1, x equals 1, notice we then flip again to being like a cup facing up. So we really have learned something. This is exactly right. All of our work from the previous thing gave us exactly what we wanted. Cool. Let's do more. Okay, so we had a first derivative test. Why not a second?
What about
A derivative test.
we had it? We've had one, yes. What about second?
Derivative test. So, theorem 12, the second derivative test for local extrema. Let's suppose that f double prime is continuous on an open interval containing a point C, at which f prime of C is equal to 0. If f double prime of C is greater than 0, then f has a local minimum at C. If f double prime of C is less than 0, then f has a local maximum at C. If f double prime of C is equal to 0, then the test is inconclusive, and we can't tell whether or not f has a local maximum, a local minimum, or just nothing like that, nothing of the sort at the point C. So this is one of those tests where you can get good results, but sometimes you don't really get much results at all. So this is basically just summarizing the obvious fact that if you've got a parabola or something that looks kind of like a cup facing down like this, and you look at a place where the tangent line is horizontal, then since this is a cup facing down, this is what something like f double prime of C less than 0 would measure. We know that this is a local max. Similarly, if you got a cup facing up, another parabola or something that looks sort of like one, and you've got a 0 slope tangent line at some point, then the fact you know that it's a cup facing up tells you that that's a local minimum. This is when f double prime of C is greater than 0. And that's pretty much it. Sometimes you can get stuff where neither of them really goes. Think of, for example, x cubed, something like this. Here, I'm switching from being a cup opening downwards to a cup opening upwards, right? You know, this little guy versus that guy. And I also have a flat tangent line. So I will have a switching concavity. I will have a 0 first derivative. I'll have a 0 second derivative from that switching concavity. And I don't have a max or a min. So sometimes, because of things like this, you don't always get what you want. But if you try sometimes, you can at least figure stuff out like this. You can maybe get what you need. Yeah, cool. Let's look at an example. Okay guys, example 11. Let's use the second derivative test to locate the local extrema of the function f of x equals 3x to the fourth minus 4x to the third minus 6x squared plus 12x plus 1, the same weird old quartic we've been looking at, on the closed interval from -2 to 2. Okay, fair enough. Let's try it out. So we considered this guy in example 6. We considered it in example 8. We found the first derivative. We found the second derivative. And I've got them right on the screen for you right here. Let's not bother going through and just saying them again and again and again. Let's get into the actual meat of it. So, on to what's really going on to what really matters. So, we know the critical points are at x equals -1 and x equals 1. That comes from this first derivative. We know this first derivative and we can handle it. We can figure out its zeros. This gives us critical points. Easy enough. We evaluate the second derivative, which we've got just sitting right here at the critical points. We'll find that f double prime of -1 is 48. It's bigger than 0. So by the second derivative test, f has a local minimum at x equals -1. At the critical point 1, f double prime is equal to 0, and the test is inconclusive. The first derivative does not change sign at x equals 1. This does mean that f does not have either a local maximum or minimum at x equals 1. Let's look at the graph and make sure we've really got this down. Okay guys, here we are back to this graph yet again. What we saw just looking at the second derivative test is that at -1 we had a local minimum. That's this guy right here. So we're at -1. We can see that we're concave up. We've got a 0 first derivative. And so we got a local minimum by the second derivative test. Now when we fly on up on over to x equals 1, just right over, oh gosh, so hard to seek. There we go. Right over about here, you know, in this little zone, yeah? When we fly over here, we can see that we don't have a max or a min. This is basically the x cubed situation. We've got positive slope tangent lines right on up to that point, then they're 0 for a second, and then they keep being positive. We also change concavity. We go from looking like a cup facing down to a cup facing up. And so we're changing concavity. We've got a 0 first derivative, but we're not changing the sign of our first derivative. So we can tell that this isn't going to correspond to a local max or a local min. Because if there's one thing we know about maxima or minima, if you're decreasing first and then you hit a critical point and then you start increasing, that means it's a minimum. And if you're increasing and then you start decreasing, that means it's a maximum. If you don't do either of those, it can't be either of those. You're increasing, you take a little break, and you keep increasing. The place where you took a break can't be the highest part. You're going to keep increasing right afterwards. So, dead right. Second derivative didn't do us wrong, showed us exactly what was going on. Neat.
Yeah, this album dedicated to all the teachers that told me they never amount to nothing. To all the people that called me on arithmetic errors and missed parentheses, docked points on me when I was just trying to derive some functions and get my grade up. And to all the mathematicians in the struggle, you know what I'm saying? It's all good, baby, baby. It was all a dream. I used to derive functions as a teen.
おめでとう